All right, time to start. Welcome everyone, thanks for coming. So the next hour or so, I'm going to show you some of the stuff that's decoded in the air surrounding us all. So I was thinking this morning about maybe renaming my talk to stuff the NSA doesn't want you to know that's in the air around you, but for some reasons I decided to just stick to this. So what will be the practical value of the things I will tell you in the next hour or so? Probably close to zero. Will it be fun? I hope so. So my name is Bert Jan Schrijver. I'm a software craftsman at JPoint in the Netherlands, where I usually work on serious stuff like continuous delivery and DevOps. And by now and then you need a break from the serious stuff. So that's where this project was born. So in my spare time I'm also a JUG leader for the NLJUG, the Java user group. Any NLJUG members in here? Yep. All right, awesome. And the last one coming in, so welcome. The agenda. I'll be explaining the background of my project, explain what software-defined radio is. I'll go into the details of ADSB and AIS, what it is and how you can decode it. There will be lots of demoing throughout the presentation, and there will be lots of room for questions and answers. So feel free to use the app to post questions online, or if you have a question, just raise your hand. I'll be happy to answer them halfway through the talk. So how it all started. As I said, I work at JPoint, which is a small Java consulting company in the Netherlands. We usually work at clients, so we don't see each other that often. So a few days each year, we gather around with the whole team for a day of hacking on a project to our liking. So this can be an open source project or some proof of concept for a customer. So one of those days, one of my colleague, Roy, who's actually standing there, the tall guy in the shirt, brought his Raspberry Pi and some other stuff and some antennas and some USB sticks. And he tried to receive signals from ships that were passing by our office. It looked like a really cool project. He ended up spending most of the day trying to compile everything on his Raspberry Pi and going home with almost everything compiled on his Raspberry Pi. But still, it was a fun project, and it inspired me to start looking into this. And what he was showing me was basically software-defined radio. So software-defined radio is a radio communication system where parts of the system are implemented in software. And cheap USB digital DV sticks usually work this way. When there's a specific chipset in there, a Realtek chipset, you can even tune these sticks to a frequency of your liking. And that enables you to do all kinds of cool projects with this stuff. And you can pick them up for like $7 at Chinese electronic sites like AliExpress or Devoxx. And there is a whole ecosystem around these types of sticks. So there's a Realtek chipset, you can do software-defined radio with them. So that's what I called RTL SDR. I've never understood why Realtek is shortened as RTL, by the way, but that's out of the scope of this talk. So you can find anything about this at rtlsdr.com. There are lots of cool projects and info on there. So the sticks I'm using are these two. They're just regular small digital TV sticks, the ones you can use to receive the free-to-air channels. So you can pick these up at various sites at very low cost. They used to be around $7, maybe they're 8 or 9 by now. So I'll be doing a short demo about what you can do with these sticks. First I'll show you some stuff I recorded at home, and then I'll be doing some live demoing. So the first one is this. The software you're seeing here is GQRX, which is a tool for OS X which connects to the RTL SDR stick, where you can set the frequency, tune stuff like I want to receive AM or FM, what's the bandwidth, what's the gain of my signal. And you can use this to basically tune the stick to any frequency between 24 megahertz and somewhat 8.6 gigahertz, and then listen to the signal. So these are some amateur radio guys who have large antennas on their roofs and transmitting stuff throughout the country to each other, which is a signal I picked up. And it looks like they're trying to fix a Linux computer and discussing this over their radio.
We zien Windows niet meer in grub van Linux. Ik zit in de BIOS, Simon. Ja, oké.
So apparently he's in the BIOS, and Simon is very much okay with this. So next thing is basically the same, but on another frequency. I live near Utrecht in the Netherlands, and I live very close to the Amsterdam-Rijn channel, which is one of the busiest channels in the world in terms of traffic ships. So a lot of traffic vessels pass by there, and they have communication with the stations on the shore. So there's a shore station which coordinates the traffic and makes sure that the ships don't bump into each other. So this is an example of communication from a vessel to shore I picked up.
Boot 8, de Maas, u gaat vlak achter die Fortuna het Merwe-kanaal in over? Ja, dat is wel de bedoeling. Ja, boot 8 begrepen. Noord-Hanna, zegt de Maas over.
So this big, well, you could call it burp at the end of each transmission, actually has a name. It's called the ATIS fart. And it's it's debatable whether this sounds like a fart, but it's definitely a noise. And this is an example of a digital transmission. So when this is a communication with a maritime, which is basically a portaphone, but then for underwater. So every time you transmit something, when you let the press to talk button go, it sends out a digital transmission with the identification of the sender. So ATIS stands for Automated Transmitter Identification System, and there's the code, the registration code of the sender is transmitted there. So there's a difference between analog signals, which you can just listen to, and digital signals, which somewhat sound like farts. But there's more. Who in here has had a pager? You know, a small device which displays a number? Let's do a show of hands. All right. So keep your hands up for a few seconds. If your hand is not up, please applaud for the cool kids of the 80s. All right. So you know these pagers. I wasn't aware that they were still around, but it turns out they are. So how this pager protocol works is called POCSEC, and it's basically a digital transmission where a centralized or maybe even decentralized server sends out messages. It's a digital message, and the ID of the receiving pager is encoded in the message. So a good behaving pager only listens to messages with its own ID in there. I've created a bad behaving pager which just receives all messages, and you can see some examples here on screen. It turns out they are used for all kinds of monitoring stuff. So you can see Nagios alerts on here, some problems with pressure valves, or I didn't look into it that much, but these are still used for monitoring. So either someone is using this frequency for transmitting text messages, or they're still in use and our system administrators running around with pagers showing these messages. But there's more. There's another pager protocol which is called Flex, and Flex is used by the emergency services in the Netherlands. So this is in the Netherlands called P2000. When you look it up on the internet, you can see all this data on there readily available. But this is also kind of text message that's sent out by the central for the firemen or for the police, and is received by the devices in the cars. So you can see all kinds of stuff here, like there's a cat in the tree at that street. I believe it's all right to receive this and decode this. It's not all right to act on this information. So when you go to the neighbors to watch the cat in the tree, you probably shouldn't be doing that. So some more demoing. I'll show you how GQRX works. It's basically a generic radio receiver. So you set the frequency at the top here. You can do tuning here. You can set all kinds of filters and modes on the signal. For example, FM, AM, and other stuff. You can control some stuff in the input. For example, I've set the gain here to automatic, which means that it will send the strength of the receiving signal to the best possible value. And you can tune the squelch, which is the noise suppression level. So, any ideas what signals might be in the air around here? Probably you all have or maybe had a receiver for a analog signal in the air for a long time. It might be on your somewhere in your living room or in the bedroom. Any ideas? Just shout. A radio, yes, just a plain old radio. Radio is usually around, I think it starts at 88 megahertz. So let's see if there's something in here. That's right, so this is what a radio signal looks like.
Your words cut deeper.
I'm going to look for another station. Let's just take a minute. I told you you would have a relaxing session. I hope this helps. It couldn't have been timed better, right? So this is just analog radio, but there's more. There's all kinds of signals in the air, but there's one that I'm able to show you right now, and one I'm transmitting myself. Any ideas? Voice. Yes, I'm transmitting my voice, but how does my voice end up in the air? Well, just by my throat and stuff. But how does it end up digitally in the air? Sorry? Yeah, the cellular network is one, but I'm not on my phone right now. Microphone, yes. My microphone is transmitting a wireless signal. So I'm not going to show you the signal of my microphone because that would kind of be senseless. But I will try to see if I can find a signal of any of the other speakers in the rooms besides me. So I happen to know that these are somewhere in Belgium, somewhere around 522 megahertz. So let's see what we can find. You typically will look for these kinds of bumps in the signal. And there's one right there. Let's see, try again. Ah, there's one. So this is probably from a room where nothing is going on, since it's kind of silent. So let's see what we can find. What more we can find. I'll tune them to squelch a bit so you won't be annoyed by the noise. So what you will be looking for is peaks in the signal. So here are a few, and you can see the audio signal already appearing here. So let's see if I can tune in there. Not really. I'll just keep looking. So let me just look them up because I wrote them down already. All right, 566. So far for the surprise. Sorry about ruining it. Well, there's a nice large peak, right? Let's see what we can do with that.
What you want to create is a safe space for people with ideas, and there's these budding ideas that are very delicate, like little flames, in the beginning.
All right, this must be the startup track, It's judging from the guy's voice. So let's just take a minute to listen to this.
Make sure that in the beginning, that's easy to get into. Now, on the other side of things, remember this: the very first touch that a person has in a project, that's them testing you. Okay, you have to realize that you're being tested. As soon as you see something for the very first time, they have a question, whatever it is. They want to see how you respond. They're testing. They're gonna if this responds.
This sounds like a good talk. So let's continue. So there's all kinds of stuff in the air that you can do, and the analog signals are fun to receive and to listen to, but there's also a lot of fun in the digital signals. So we're in this talk for almost 15 minutes. I promised I would tell you something about Java. So how about Java? How can we connect with Java to the RTL SDR stick? Well, that's something we can use. It's called RTL TCP. It's a small C utility you run on your machine. It connects to the RTL SDR device and opens up a TCP socket where you can connect to the device. So you can connect with Java to the TCP socket, set the frequency, set a few other parameters, and then start listening to the stream and pick out the data you're interested in. So that's where our first target of digital signals comes into play. And this is called ADSB. ADSB is an international standard for commercial airliners. It's called Automatic Dependent Surveillance Broadcast. Probably was the term was probably invented in America, judging from the length of it. And it's used for monitoring and collision avoidance. So every commercial airliner is fitted with an ADSB transponder, which sends out, I think, a few times each second information about the position of the plane, the heading, the speed, the altitude. So planes usually know where they are, what their coordinates are. That's pretty useful when navigating. So they're connected to GPS, and they know what their position is. They also know what their speed is. So they send out their position and their speed at regular intervals. This is used for collision avoidance between planes, but also for communication from the air to the ground, for traffic control, for example. So we got our RTL SDR stick. We know the frequency of ADSB, which happens to be 1090 megahertz. We got RTL TCP running. We can connect to the RTL TCP socket with Java. Now we need to do something with the data stream. So I was looking on the internet and seeing if there was anything I could use to decode I think it's called a mode S signal from ADSB transponders. I could find a few, but they were all closed source. So they're of the type where you download a jar, you put it on your machine, you fire it up, and it will start sending data to some centralized server on the internet. Actually, if you're familiar with sites like planefinder.net and flightradar24, that's how these things work. They have just boxes all over the world receiving the data and sending it to a centralized service. But I couldn't find any open source Java decoders, and it looked like the only option I had was to run my own decoder, which I really do not fancy, since signal processing involves all kinds of difficult bit shifting stuff, and it's something I really do not want to do. So is this the only option I have, or are there other options? We got Java. I know Java, but it's closed source. There are only classes and jars in there, but I would like to have the source. Any ideas? Decompile it? You sure? All right, let me do that again with the audio on, because I heard it there very soft. Oh, yeah, here it goes. Well, let's play that again. Just rewind. So closed source and stuff, and really no other option than decompile it? Are you sure? Of course, decompile it. So decompiling is where it gets kind of shaky. Decompilation isn't exactly legal in each way, and it differs across countries. So I've looked this up. Don't trust me because I'm not a lawyer, but it seems to be illegal to decompile code for debugging purposes, to provide yourself with support for a piece of Java code. It's certainly not legal to decompile something and then integrate it in your own product. So I'm kind of going to leave into the middle what I did here. Leave it as an exercise to the viewer. So this is the first setup of my system. So I got the ADSB antenna. It's connected to an RTL SDR device, plugged into my laptop, running the RTL TCP server on there, running a piece of software I won't describe in too much detail that decodes the signal and then feeds it into MongoDB. Why MongoDB? Because I like MongoDB. So the MongoDB serves as a database for all the ADSB position events I've received. There's a small web app built with Jetty and jQuery and Google Maps, which sends out the data, and you can access it with your laptop or mobile phone. So demo time. I was at the parking lot this morning, right in front of the venue here, trying to receive signals from some planes, because that's a nice open space, and when you want to receive a radio signal, it works best when you have a line of sight visibility between the sender and the receiver. So when you're out in the open space, you got the best chance of receiving those signals. So you're looking at a map of the Netherlands here. I believe we are not in the Netherlands, but a bit more south. So here we are. We're currently in Antwerp, which is here. And the red lines are paths from planes. The black dots are actual positions of the plane. So let me rewind this a bit. Let's see. Yeah, so this is the actual state of air traffic above Antwerp at 10:39 this morning when I was outside at the parking lot. So this is an actual view. So what you can see here is that there are planes flying above Antwerp, which is not really a surprise. What you also can see is that the range of, I just used this simple antenna to pick up the signal, but I find the range pretty impressive. So when I show the complete amount of data I gathered this is from half an hour. I was half an hour in the parking lot, poor me. So there's even signals through Dordrecht, where I was born, going to past Brussels and to Luik and even almost into France. So that's a pretty impressive range for such a small device. So this is all drawn using the Google Maps API. This is a small front end that connects to a backend that basically serves out the data from MongoDB. So there's a request every second or so, which returns a list of positions. I'll be showing some more details on this later. So that's what you can do with a bit of Java, a bit of JavaScript, and a small Chinese stick. That might have sounded a little weird. So how does the data look in MongoDB? This is basically a JSON representation of the ADSB messages. So there's a heading in there, a position, object ID, object type. No idea why that is in there. Maybe we'll learn that later. There's a timestamp and there's a date when it was created. So this is basically the result of the processing of one ADSB event and sending it into the database. So then on the API structure, it has some from and to feeds to filter, so you can look at a specific time in the past. Then it sends out a list of, for each aircraft, it sends out a list of positions. And I see that this is one of the most badly named APIs I've ever seen, since there's a positions array with objects in there with arrays of positions. So you can see why this is a hobby project. I would get killed if I would do this at work. So one of these blocks is just all the information I need to draw this red line with this black triangle at front. So it has a current heading, it has an object ID, which is the flight ID, it has a timestamp, and there's a list of positions, which is basically latitude and longitude coordinates I received. And then I let Google Maps draw a flight path over these coordinates. So the Google Maps API is pretty simple. You draw markers and polylines. So a marker is the black triangle, which stands for the plane's position, and the polyline is the flight path, which gets fed an array of latitude-longitude tuples. So that's cool. Well, at least I think it's cool, but it's not really optimal to run this in your house because usually in a house you don't have a line of sight visibility with airplanes. If you do, you either start running or you're missing your roof. So in my house there's a roof and there's I don't see many airplanes from outside my window. It would also be nice to have an always-on service, to run it on a server of somewhat, and I need my laptop to do work now and then. So let's design a revised system. We're getting a bit more serious. So when receiving radio signals, it's important to have a good antenna. And a good antenna is best tailor-made to the signal you're trying to receive. So I looked this up on the internet. Of course, I didn't think of it myself. But an optimal antenna is one with an optimal pole length tuned to the frequency. So ADSB is at 1090 megahertz, and I think I made my antenna using a quarter of the wavelength of 1090 megahertz. So then it's pretty small, it's like this size, and it's optimal for receiving signals. So I'm hoping this doesn't show up too well. You can all see my brilliant soldering skills on that screen there. It's just pieces of copper made together to a coax connector, which goes into the ADSB, to the SER device. So then there's a shed in my garden with a Raspberry Pi in there. Why? Because every project gets cooler when you throw in a few Raspberry Pis, right? So Raspberry Pi sits in my shed. The antenna is on the roof of my shed. Raspberry Pi is connected to Wi-Fi with my home network. It's running RTL TCP client, and my Linux box at my attic is connecting over Wi-Fi to the Raspberry Pi. And the system is available over the internet. So that's all fine and dandy, but there's a but, of course. We're halfway to the talk, I must have more to tell you. And I do. The raw stream from RTL TCP is pretty huge. So I had problems getting this to work at first, because it turned out it was something like 30 or 40 megabits, just sending the raw, basically audio stream to over my network. So I bought a faster Wi-Fi stick. Traditional solution, just throw more hardware at the problem. But still, things could be better. And I would also like to give AIS, which my colleagues tried before. I would like to give it another try. And I want to throw out that whole piece of code, of which I do not disclose details with you. So what can we do? Actually, I did this talk before at JFO in the Netherlands, and this was a suggestion from one of the audience members. He said, why don't you just decode the signal on the Raspberry Pi? It turned out that was a great idea. So now I'm running another utility, which is called dump 1090, which is a C utility, running on the Raspberry Pi, connecting to the RTL SDR stick, decoding the ADSB signal on there, and then just exposing the data over HTTP through a REST interface. The rest of the image is still the same. So dump 1090 has a small user interface look like this. So this is basically the data it gathers, and it also exposes this on a REST interface. So in the revised system, I can now connect from my Linux box over the network, over HTTP, to dump 1090, fetch the data from there, put it in the database, and continue. And now only the JSON messages are transferred over the network, so the network load is a lot lower. All right, so before we dive into AIS, any questions so far? Did anyone use the app yet? I'm curious. No one. All right, so you got the chance to be the first at the next question round. So, time to hop on to AIS. AIS is basically kind of the same as ADSB, but for ships, or vessels, or boats, or whatever you call them. AIS has two types. There's Class A AIS, which is used for large traffic vessels, and there's Class B, which is used for smaller pleasure crafts. And these ships are equipped with a GPS receiver, so they know where they are, they know what their position is, what their heading is. They transmit this over a radio signal so that other ships and shore stations can receive this signal. So actually this is not the primary collision avoidance system for ships. Anyone knows what the primary collision avoidance system for ships is? Yes?
A radar.
A radar, yeah, of course. But radars are pretty expensive. A radar will easily set you back like 3 to 10 grand, even on a pleasure craft. And AIS responders, you can pick them up for, I think, 300 euros and upwards. So AIS is pretty cool. Most pleasure crafts are equipped with a chart plotter, where it's just like Google Maps for your boat, and the AIS data is displayed on there. So when you're sailing in bad weather or at night, you can see the other ships around you that have an AIS transponder. So how can we integrate this in the system? Through a slightly altered chain of events. We have an AIS antenna, which is a different antenna from the ADSB antenna, since AIS is on a different wavelength. It's somewhat like 167 megahertz, I think. It's connected to the Raspberry Pi. On the Raspberry Pi is running RTL FM, which is a utility that converts an RTL SDR data stream to an audio stream. So you could just plug in your headphones and listen to the audio signal. Then RTL FM feeds the audio signal over a Unix pipe to AIS decoder, which is a small GNU C utility that can decode the audio stream into AIS data. And then AIS decoder sends the data over UDP to AIS messages, which I will be telling a bit more about. So the first 3 stations of the stream kind of look like this. So we fire up RTL FM and then pipe it to AIS decoder, and then you see these AI VDM messages appearing. And these are, this is a standard, it's called NMEA. NMES is standard for inter-device communication on nautical systems. So when you have a sailing boat with a chart plotter and a speedometer and a log, which logs how far you're going, these devices communicate with each other through NMEA. This is an example of NMEA messages. So now the final step is to convert these messages to something I can put into MongoDB. And the fun thing is I did a preliminary version of this talk at Devoxx last year as an Ignite session, so I crammed all this in 5 minutes and talked really fast. But the AES part wasn't in there yet. And after that session, I was in the tram back to the hotel, and there I met a gentleman, Thomas Borg-Salling, who's actually here. Can you wave to the audience, Thomas? There he is. And I was explaining what I was doing, and he said, well, that's funny. I'm basically doing the same thing, but then for ships. And I've created some software for this. You should look into this. And I was like, well, that sounds cool. Let's see if I can do this. And went back home and started looking into this and got to the part where I need to decode the NMEA messages. And then I started looking on the internet for some open source libraries to decode these messages. Fortunately, there was one. I integrated, started looking into it, and then thought back, oh, well, wait, I met this guy in the tram, and he was saying that he created something, so let's look him up. And I looked him up, and from there saw that I already had grabbed his library from the internet and was already using that to decode this. So AES messages decodes the NMEA messages, and from there up, I pick it up and throw it into my MongoDB. So, the third version of the system. It's basically pretty much the same as the second version, except that I've now added a receiver for ships. So the white bar you can see on the image left is just a piece of coax cable, somewhat like 1.20 meters in a PVC tube, which is connected to a RTL SDR stick. So the Raspberry Pi now has two sticks. One is handling the ADSB part, and one is handling the AES part. I'm sending the AES messages over UDP to the Linux box, so then the Linux box is running a Java app that is aggregating the ADSB messages and putting them into the database, aggregating the AES message and putting it into the database. So it's time for another demo, and I'll be demoing now over the internet from a system that is running at my Linux box at the attic at home. So, and that's this. Let's zoom in a bit. As you can see, there's currently being data received. We can see, and let's zoom into the planes. We can see the airplanes now surrounding my house. And the fun thing is that I live quite near to Schiphol, which is a large airport in the Netherlands. And when I go back a bit more and take the data from the last 60 minutes, you can see these funny paths appearing around Schiphol. So these are probably either approach or departure paths defined by the Schiphol airport authorities that all planes need to follow. So when I crank it up a bit and take data from the last 2 hours, you can see these paths forming. So here's actually one flying right now. This is the KLM 71H. When I click this little thing, it links to Plane Finder or something like that. And let's see if Plane Finder agrees with me. Look, it's the KLM 117, which has just taken off from Amsterdam. So what have I proved now? Well, basically that I can do myself what Plane Finder does. Not a big deal, but it's a fun project. As I said, there won't be any practical use for you in this. So as you can see, there's a lot of air traffic going on around the Netherlands. Amsterdam is a busy airport. So let's look into ships. We don't see any. And as a matter of fact, I don't see any since somewhat this morning, 9 a.m. or so, 9:28. And I think that the antenna that was in my attic, in the attic window, has fallen over. Since I'm moving and, we're shoving boxes around at the attic, and probably it broke or fell over, pulled out the antenna. What we can see is that there was a boat sailing here this morning. And this is its call sign, and this is actually the same. Is this readable? Yeah. This is actually the same identifier that's being used in the ATIS FART. When you have a maritime communication with another ship and an AES receiver, you can actually see where that ship is. So let's take a bit more data, and let's go back like a few thousand minutes, or even more, and then we might see some stuff appearing. So actually, there was a boat here that I went from the Amsterdam-Rijnkanaal onto the Vecht, then went here, and then crossed land here, and then got second thoughts, turned around, and crossed land again. Is this an amphibious boat? No, probably not. So what I'm doing is just creating a feed of all data points I received, all positions, and then telling Google to make something out of it, draw a line. So probably I just received some points here, and then couldn't see it anymore here. And then I picked it up again here and here and here, and then somewhat here again. So I can assure you that this boat probably didn't travel over land, but I am curious what boat this is. This might be the party ship that's located close to my house. Well, you can definitely have a party on there, but it's not the one I meant. It's towing a houseboat here, actually. So probably this is working on the canal, on improving the borders. There was another one here. There it is, party ship MS De Tijd, crossing the lovely town of Maas right here. So this is situated in the harbor quite close to my house, which is somewhat here. So actually this probably just came back and then went on with another party team to go up on the Vecht. So we can see quite some movement going on here. Let's take a bit less information. That's still a bit much. So you can see some movement going on. There's also a harbor here where traffic ships dock and get unloaded. So this is where you can see ships moving. This is actually a few days ago. Let's see which this one was. Probably a freight ship. This was the mystery tanker. Probably had a good time there on the Amsterdam-Rijnkanaal. So back to the presentation. Well, we were in 2015. Everybody loves data, right? Who loves data? Okay, half of you love data. Well, the other half just lay back and enjoy. So I got my system running for a while. I'm keeping all the data it receives for about a week. There, I think I put a self-destructing index in Mongo. That's deleting everything that's old in a week because my disk kept running full. So I got myself a nicely stocked MongoDB with plane coordinates and with ship coordinates. Now what? We can visualize it. So let's see how this looks. The antenna range for planes. I found this interesting. It's quite this is quite a large range. It covers most of the Netherlands, about half of Belgium, and also onto the North Sea. So this is just an antenna that's this big, standing in the room in my attic, receiving signals from up in the air. So what you can see is that there's a lot of I can receive a lot of planes towards the west. But not so many data towards the east. Most of them ends somewhat like 5,200 kilometers to the east. So why is this? If you look at the map, you might understand. Let's see if I can explain. So my house is situated somewhat parallel to this road. And my house is here and my shed is here. So it has a clear view in this direction out of the attic window. While the other side, my house is kind of in the way. So when we go back to the image, the antenna has a clear view. Let's see if I have a pointer on here. Yeah, although it doesn't go that far. The antenna has a clear view this way, but this way it can only view to the roof and then through here. So when a plane is here, not that close, but 100 kilometers away, it won't see it because the signals will get blocked by the house. So that's probably, I'm just trying to explain the picture, why I can see a lot to the west, but not too much to the east. The antenna range for ships is a bit less. It's a few kilometers, and it's harder to get a line of sight visibility with a ship because there are houses between my house and the canal. But for ships, that's not really a problem because when you are an airplane and there's another airplane, say 3 kilometers away, and you're detecting that there's a risk on collision, you better change your course very quick. When you're on a ship, there's another ship 3 kilometers away, you're detecting collision. Well, you go make some coffee, you go to the toilet, you read a newspaper, and then like half an hour later you change course a bit, and then you're good. So that's why the range for ships is a lot less, but still it's pretty good. So let's take a look at how much data the system receives in an hour or in a few hours. So I'm just looking at data from planes here. This is 1 hour, and you can see the same flight patterns evolving on the screen here. 2 hours, there's a bit more. 4 hours, it's getting crowded above the Netherlands. And every black dot is a plane. So this is all already, I think, maybe a few hundred planes even. 8 hours, Netherlands are turning red. 16 hours, and then a whole day you can't see the Netherlands anymore. So that's quite a lot of flight movements above my house. Lots of planes that are in line of sight with my ADSB receiver. And I'm omitting everything that I'm not receiving. So that's a lot of flight movements. All right, to summarize. Now wait, before we summarize, let's see if someone asked a question. Nice talk, you're welcome. How long do you look on the map during 1 week, 1 month? I'm not sure I understand the question. I usually look at the map for a few seconds and then start doing something else again. But I don't think I understand the question correctly. But I'm keeping data for a week, and well, I think I probably am starting to understand the question. So I'm keeping data for a week, and what you see here is every position I received for the time window of the system for a specific plane. So, for example, when I go to the demo, go to planes. Let's change this first, otherwise it will be getting in lots and lots of data. So planes in the past 15 minutes. So what you're seeing here now is actually, yeah, here is all the data received in the past 15 minutes for these planes. And as long as I've received a data point for a plane, it's on the map. So when I set this to 10 hours, you see all the data I received in those 10 hours. It takes a while to put it in. And the position of the black triangle for the planes is the last position I received for a plane. So you can see lots of planes somewhat stopped in the air here above Amsterdam. That's probably just the moment where they got out of my line of sight. I couldn't receive them anymore, and that's why they are stopped on the map here. They're probably not still above Amsterdam here altogether. So, how many hours of fun did I have setting up the system? Well, that's a good question. Quite a lot, I think. It took some time figuring everything out, and building stuff took some time. I made some iterations. I think there are easily 40 hours in there, maybe a bit more, but certainly not more than 100 hours. Can I receive GSM? Probably. Well, it depends. This stick is able to receive everything from 24 megahertz to somewhat like 1.7 gigahertz. So when the GSM signal is in this spectrum, you might be able to receive it. So is there anyone here using a GSM that's in the 800 megahertz spectrum? I think it's usually 8 or maybe 1600. So you could tune the signal to it. Let's see if there's something on 1600. But you wouldn't be able to make anything out of it, because it would just be a digital data stream. So there's nothing here. Look at 800. It might even be somewhat above or below 800. But you would just see basically the GSM equivalent of a very large, long, and intense ATIS fart. Sorry about that. So you probably could receive GSM, but GSM is definitely encoded. So you need to be able to decode it, and I think that might not be legal at all. When you mentioned the removing, what will happen to the setup? I sold my house and I'll be moving to an apartment for a limited amount of time. I will probably set it up there again, but there won't be a shed involved, so I'll just need to see how many signals I can receive from the apartment. Now we are waking up. That's good. Do you have any experience using GNU Radio? Yes, actually the AAS, one of the AAS decoders I'm using is based on GNU Radio. GNU Radio is a set of tools for radio enthusiasts, and it's part of GNU Linux. Are you looking about a community to create a big map over the world? I am not, because it's already there. It's called Flight Radar 24, and I think planefinder.net is kind of doing the same. And some of these systems will send you equipment for free. You can just put it in your house and hook it up, and then you'll be one of the these stations that will be sending data to these systems. So I definitely am not going to rebuild those systems by myself. Tried receiving weather satellite images. I did not. I think Roy, you tried. Did you? All right. So, but you said it would be possible. There are instructions on the internet how you can do this. So it's definitely possible. I haven't looked into it. How many visitors does your site have from the Middle East? Yeah, that's a fun question. Not that many, I think. I haven't looked into this. But you know, this information is already readily available on Flight Radar and Planefinder. And when you want to do something where you would want to know where a specific plane is, you can just look onto those sites. So what about sending? You cannot send signals with this device. Is just for receiving. So that makes it a passive system, and that makes it that you don't need a license to send out signals. So there are devices you can buy for I think there might be something like $20, where you can receive signals, but then you would need a license. And licenses are usually for a specific bandwidth or a limited spectrum of bandwidths. When you would buy such a thing and start sending out ADSB messages from your house, probably you'd have a visit from some authority quite soon. So can we see some code? Yes, it's on the last slide. Can you use the FM tuner of a smartphone to decode IAS? I don't know. Haven't tried it. Thomas, have you tried it? No, okay. Well, there are actually, I've seen some software for Android where you plug in RTL SDR device in your Android and decode stuff there. So it is possible. Do you listen to police radio? I am not going to comment on it, but it is possible. All right, so I think that's about the questions we had. I'll give you another chance in a few. So to summarize, playing with software-defined radio can be fun. It can be loads of fun. You can get started for just a few bucks. When you order one of these devices at Devoxx, it will take like 8 weeks for them to send it to them over the sea, but still you can get them for very low cost. If you want any details, all the source of the stuff I showed you, including instructions on where to buy devices, how to decode POCSEC pager messages, and set up this whole system, it's all on my GitHub page. So it's on there. Even instructions on setting up your Raspberry Pi in a database, you can all look it up there. As long as I'm not moved, which I will be doing in the next few weeks, there's a live demo at sdr.revolution.nl where you can view the system I just showed you. And there's lots of info on cool SDR projects at rtlsdr.com. So we are already in the Q&A. Let's see if there are any new questions. There aren't any new questions. Are there any questions from the live audience at the moment? We have some time left. Everyone is satisfied? There's a question here.
How is the idea of listening to plane position and boat's position came to you? Is that something like before?
Yeah, so how did I get the idea of listening to those positions? Basically because Roy showed me that it was possible, and that interested me. And I was also very interested in trying to get to know a bit more about all the stuff that's in the air surrounding us, and how you can do fun stuff with this. So any more questions? All right, so I hope you enjoyed. I had a good time. You were a good audience. If you liked it, please vote. Vote honest in the Devoxx conference app. If you have any questions, you can reach me on Twitter. I'll be happy to help, and I'll be around for a few more hours here. So thanks a lot for your time. You were a great audience, and see you around.